topic which we are going to cover in this video tutorial happens to be special matrices. Let's look at the definition and application of a special matrix. So one condition for the matrix to be a special matrix happens to be it should be a square matrix. This is the first condition, and based on that we have diagonal, tridiagonal, lower triangular and upper triangular matrix. Now the diagonal matrix, we say that M is a diagonal matrix. Suppose if I is not equal to J, for I not equal to J, if M of Ij is equal to 0, and for I is equal to J, M of Ij will not be equal to 0. So this has only diagonal elements. Other elements other than the diagonal will be always 0. The simplest definition of diagonal. In tridiagonal, which is 3 diagonals, we have a main diagonal with elements. If we consider 4 by 4 matrix, so the elements indexes would go from 1 1 2 2 3 3 and 4 4. They will be our diagonal elements. Over here we will not begin the index position from 0 0. Rather than that, we will always think as if the index for a matrix starts from 1 1. So tridiagonal matrix, the definition goes like this: M is tridiagonal if and only if M of Ij is equal to 0 for magnitude of I minus j greater than 1. To make this concept understand, let's try to work out with an example. Let's assume that you have a 4 by 4 matrix with the index starts from the first row. Indexes are addressed as 1 1, 1 2, 1 3, 1 4. Second row index positions 2 1, 2 2, 2 3, 2 4. Third row 3 1, 3 2, 3 3, 3 4. Fourth row indexes 4 1, 4 2, 4 3 and 4 4. Assume this are the index position. Now let's work upon the first example or second example. What is this? Magnitude I minus j greater than 1. So let's assume I and j value to be equal to 1 1. So in that case, magnitude of I minus j, is it greater than 1? No, it is less than 1, which means at that particular position of the index, the value of M of Ij will not be equal to 0. It will be non-zero. Similarly, if we do take the value of I as 2 and j as 3, we are referring M2 3. What is the second row third column? Second row third column element, we have a value, and that indeed is a element belonging to tridiagonal matrix. That again is a tridiagonal matrix. Why? Because magnitude of I minus j is not greater than 1, it is equal to 1. So I we had taken it as 2 and j we had taken it as 3. So we have 2 minus 3 becomes minus 1. Magnitude of minus 1 becomes 1, and indeed it is not greater than 1, it is within 1. So that's a non-zero element. Now we take one more example wherein I'll take a value of j as 4 and value of I as 1. That is first row fourth column. First row fourth column. So what happens to magnitude of I minus j? So it becomes 1 minus 4 and you get 3 here, and 3 is definitely greater than 1, which means at that particular location the element is equal to 0. So this is not a tridiagonal element. That doesn't come under tridiagonal event. Similarly, we can take one more example wherein I value is 4 and j value is 1. So it would be fourth row first column element, and that again is not at any cost, it is not a diagonal element. So there again the value will be 0, due to which we have this condition: magnitude I minus j greater than 1, which means the difference between I and j will be I might be equal to j plus 1 or I might be equal to j minus 1. That would be the difference. that is the case, then it will always be located in the diagonal, three diagonals. Then you have lower triangular. The way you define lower triangular matrix as m of ij is equal to 0 or I less than j, and m of ij is equal to 0 for I greater j for upper triangular. Let's try to understand this with an example why it is a lower triangular and upper triangular. For the lower triangular, you can consider example 7.7c, wherein the elements, I'll read it as, it is 2 0 0 0 first row elements, second row elements 5 1 0 0, third row elements 0 3 1 0, and fourth row elements 4 2 7 0. Okay, now let's try to work on this formula. I less than j or I less than j, m of ij should be equal to 0. Now when we go to the first row, last position, the value of I is 1 and the value of j is 4. So I is less than j, so there the value is 0. That's correct. Similarly, we will take I as 1 and j as 3. Okay, so I is definitely is less than j there, right? Then again there the value is 0. So you can focus on lower triangular matrix, which is 7.7c and 7.8c figure. 7.8c has a specific 4 by 4 matrix with the elements as I have addressed before. So this makes sense. Always the condition is for I less than j, the elements m of ij elements will be 0, and only for I greater than j, greater than or equal to, the m of ij value will be non-zero. Okay, now we will take the value 5. 5 element happens to be located at second row, first column. That is for a lower triangular matrix. So what is the value of I? I is 2 and j is 1. So I is greater than j. So there the element is non-zero. Okay, so that's how you define lower triangular. Similarly, the reverse is applicable for upper triangular, and we will not discuss this. You can focus on example 7.8d. You can take that example and you can explain. For all values of I greater than j, where strictly I starts from 1 and also j starts from 1, I greater than j condition, m of ij will be 0. Lower uh, it's a lower index, lower elements below, lower elements below it is diagonal. So we will move on to the next slide. This we have discussed. This example you take, better you make a note of diagonal, tridiagonal, lower triangular, because we will be using this matrices, this 4 by 4 matrices in future for making you understand the program. We will be using this. So let's try to use the same example. Okay, so 7.8a, 7.8b, and 7.8c I need later. Okay, let's work with diagonal matrix. Now the diagonal matrix, we know for I is equal to j, you have element at I is equal to j position. I not equal to j position, you don't have any element. Now how is that you going to design data structure for your diagonal matrix, and what and all components we need to utilize? So diagonal matrix name matrix it is, but majority of the elements are 0. So only non-zero elements, if you consider, that's fair enough. And to consider the diagonal matrix non-zero elements, we require a variable here to hold the data belonging to the diagonal elements. To hold that data, we use a variable element here, and its dimension should be equal to the square matrix dimension size. Square matrix, not m by m, it is just m. How many number of rows or how many number of columns you have, that number if you know, that's fair enough. Based on that, we will be creating a element array. Okay, so one thing, you require a private element, private data named as element, which is something like you are going to map a matrix into one dimensional array, because matrix difficult to store, two coordinates you will be having and difficult to process again. So we will always try to use one dimensional array. Cost wise, cost, as far as cost is concerned, um, it's less, that's why. Then we will move on to the program where it is discussed. So this program do concentrate have diagonal matrix. The name of the class is diagonal matrix, and this has two functions. This you call this as a class constructor. This is a destructor. Get and set are the methods, and these are your private data which you will be using, which will be processed based on this functions. So the first function, diagonal matrix, you have defined here int the n is equal to 10. What this is, suppose if you create an object of this class diagonal matrix, and if you define it as D, say that I write diagonal matrix space D in the main program. So what is D? D is an object belonging to the class diagonal matrix, and at that point I have not addressed what should be the size of D, right? So in that case, the n value will be defaultly set to 10. So matrix you create with size 10. Okay, so when there is no argument provided, default constructor will be called, and automatically it is going to set the size for the matrix as 10. Suppose if I define, second case, diagonal matrix D, and there inside the bracket if I define the parameter as 20, then this default parameter will not be used, rather the 20, the 20 will be replaced by 10. Okay, it is just to create a space with some values. Okay, so then you have a destructor diagonal matrix, so delete the complete array which was created. Then you have get method, and also you have set method. The method get has two arguments, and here this both are integer. Index positions we will be addressing, and this index position always starts from 1 1, remember. Similarly, set method again takes three arguments. These two indexes should always begin with 1 1, and one more will be the data which will be replaced by the older content. This will be the new content which needs to be replaced over the older content defined by these two coordinates. Then you have a data n, and you have a data element. N would talk about the dimension of the matrix. So diagonal, how many number of diagonal elements you have, that will be the number of value of n, and it should be non-zero. And element would be an array. So this pointer which has been created, you have to create a array with the help of this pointer element, and the dimension should be set as n. Okay, so we require this features. Thus many parameters are essential. This you call it as a data, this you call it as a function. Now this is your first class, because destructor is already defined, complete function is defined, the constructor is not defined. Okay, so what happens if you don't provide any argument to the diagonal matrix, right? You just use diagonal matrix space D, object with no argument. So here this the n value is 10, already we have discussed. Then it will be called automatically considered if the n less than 1. No, that's not the case. Then n is equal to the n becomes 10, and element will be t space of 10. So you're going to create a space for t data type template class it is. So it is something like diagonal matrix element could be belonging to any data type. So t is actually the data type here. Okay, then n is 10 here, because we have not provided any parameter to the constructor. Suppose if we would have provided a parameter to the constructor saying diagonal matrix space D, and inside the bracket we define 20, then here the n value will be replaced by 20, and that will be used, and you're gonna get an array with 20 memory locations. Okay, and that's how this constructor works. So hope this function is clear. Now let's move on to the next function, which is a get method. In the get method, the job is to use two indexes beginning from 1 1 and return the element, proper element if it's a diagonal element, or else return 0 if it's not a diagonal element. The first condition which you are going to check over here is if I less than j and or j less than 1, or I less than greater than n, or j greater than n. What is n? N is the length of the diagonal element, length of the diagonal, or it could be row size, could be column size. Okay, so suppose assume by accidentally the user enters something like 0 comma 0. So when 0 comma 0 is addressed, so you get this I is less than 1 definitely, so that condition is true, so this will be working upon, and you're going to get a message matrix index out of bounds. So this prints a message matrix dimension should be greater than 0. Please enter the valid number. If not, if then it will check whether I is equal to j. So it checks I is equal to j. I is equal to j condition. If it's, for example, let's assume that we had a diagonal matrix defined in 7.8a. So the diagonal elements were addressed as 2 1 4 6. Okay, the positions of diagonal matrices are as follows: 1 1, 2 2, 3 3, and 4 4. 1 1 position, the element is 2. 2 2 position, the element is 1. 3 3 position, the element is 4. 4 4 position, element is 6. Now when you work upon this, if I is equal to j, let's assume the positions are 3 3 and the element is 4 there. So we are supposed to get back 4, return 4 element. Okay, so if 3 is equal to 3, so 3 is equal to 3, return element of I minus j. So what is I minus j? So I minus j returns 2. So position 2 of the element 1D array. Element of 0 will have the 1 comma 1 position, 1 comma 1 location in the matrix. That element will be stored at the position 0 of your array element. Similarly, the second diagonal element will be stored at the position 1. Third element will be stored at the position 2. So on it goes. So because here we are constructing using a data structure. In the data structure, core C++ language is used. So the elements will always begin from 0 here in your data structure definitions. Whereas in your user can use positions even 1 comma 1, no problem, it works. But indirectly this function will be called automatically, and it will be the corresponding data will be stored in the data structures function. Okay, so 3, if 3 3, you get return of position 2. Go to element of 2. Element of 2, you have stored the value is 4 itself. So element of 0 value 2, element of 1 value is 1, element of 2 value is 4, and element of 3 value is 6. This way the diagonal matrix will be stored using a one-dimensional array. Mapping is as follows. Okay, similarly the next function is set function. In the set method we will use the function named set 3 arguments I, j, and new value. I will talk about the row position, the j column position, and the new value. Now let's say that the 4 by 4 diagonal matrix you have 4 comma 4th position we have 6, and this needs to be altered by 10. So what should be done here? I should be equal to 4, j should be equal to 4, and new value should be equal to 10. Now assume I 4, j 4, and new value is 10. So it checks for this condition. If I less than 1, no. J less than 1, no. I greater than n, no. J greater than n, no. So this is inside your matrix boundary. So this is false. Then you check this condition. If I is equal to j, I is 3, sorry, I is 4, j is 4, so the condition is true. So you are returning element of 4 minus 1. So what you have at element of 3 position, at element of 3 position you have a value right now as 0, correct? Sorry, it's not 0, it is 6. 6 is your value, because diagonal matrix numbers are 2 1 4 6. So sixth position, 10 will be stuck, that's all. So the value is set, this value 10 value is set, and it is replaced by the older value which is 6. Okay, and this would be for diagonal. Suppose if it's not a diagonal, then this condition will be true. So if I not equal to j, what happens? Else I is not equal to j, then if new value not equal to 0, if new value not equal to 0, which means you're not looking at the diagonal, okay, and it is not equal to 0, so new value is not equal to 0. If it's 0, then no problem, you can use, it doesn't make sense, but since this should be 0, you have again warning, or this is exception again, illegal parameter. You cannot have non-diagonal elements value non-zero, it should be 0. Okay, that's what the message will be printed. This is about the diagonal matrix. Then we move on to tridiagonal matrix. So in tridiagonal matrix, the condition, it should be a square matrix with rows into rows. We can use rows into rows rather than rows into columns, because row is equal to column. You will be having 3 diagonals, main diagonal, and the diagonal above a main and the diagonal below main. Now there will be a question, like when you're mapping a matrix, tridiagonal matrix, into a one-dimensional array, then how many number of spaces you need to create for your tridiagonal matrix? That is the question number 1. So suppose if we had 3 complete main diagonals, then we would have required 3 times the row size. 3 times the row size would have been the total capacity. But over here, only my main diagonal will consume row numbers. Okay, suppose if you're working with 4 by 4 matrix, then the total number of elements which happens to be non-zero will be main diagonal element, the diagonal above main, and the diagonal below main diagonal. Okay, so altogether it is 4 in the diagonal, 3 above, 3 below. So you have 4 plus 3 plus 3. So 10 elements. 10 elements will be non-zero out of 16 elements for a 4 by 4 matrix. That's for tridiagonal. When the number of size or the dimension of the matrix changes, then it will change drastically. And now for this condition, we will concentrate on 4 by 4 matrix. For that, capacity of your element array dimension should be 3 times rows minus 2. Let us work upon this. So what is 3 into row? 3 into row, 3 into 4. 3 into 4 we have 12. 12 minus 2 becomes 10. So 10 is actually the capacity, and that's agreeing. Okay, so this is the fact, because the diagonal below and above will take the number of elements one less than the main diagonal total number of elements. Okay, so now the mapping function which we are going to use is lowest by diagonal. What is lowest by diagonal? We will talk about this. Now for this, I repeat, 7.8b figure, you have a tridiagonal array. Okay, I'll read the tridiagonal elements. It is addressed as first row elements 2 1 0 0, second row elements 3 1 3 0, third row elements 0 5 2 7, and the last row 0 0 9 0. So 16 elements. Okay, now how this matrix value will be moved onto the one dimensional array, how the mapping takes place, and it is based on diagonal lowest diagonal. Okay, numbering by lowest diagonal. So what is your lowest diagonal? Lowest diagonal elements are 3 5 9. If you observe the 4 by 4 matrix, 3 5 9 will be the lowest diagonal elements, and the next becomes your main diagonal, there the element value is 2 1 2 0, and the last diagonal elements are 1 3 7, which happens to be the diagonal above the main. Okay, so when you take all the elements together in the order as addressed uh, previous, 359 first three elements, 359, so that's its the first positions, first three position, that number will be stored. Then diagonal elements 2 1 2 0, and finally 137. So altogether you have 10 elements, and we again, I repeat, we use lowest by diagonal mapping. Okay, now let's work upon this tridiagonal matrix. Okay, now tridiagonal matrix, uh, it is similar to diagonal matrix if you want to construct. The difference would be in the get and set method. Okay, the get method we will concentrate. Set method is not addressed in the textbook, but it can also be developed. Okay, so the get method of tridiagonal matrix goes like this. It takes two arguments. Okay, and we will work on the matrix which is discussed previous. Okay, so how the get of some coordinates gets mapped onto the array. Okay, fine. So 359, yeah, fine. So before that, you just take this information, take this information separately, also the dimensional matrix, 4 by 4 matrix, as well as this one dimensional array you can take, and we will verify whether the mapping mapping defined in this program functions properly. Okay, all three cases we will work with. Okay, and this is for lower triangular, we will check tridiagonal, we will check. Okay, so now the first condition I'll take simplest case wherein it is a diagonal element. So diagonal element is a, it's definitely, it should be a tridiagonal matrix. So diagonal elements which we have now is 2 1 2 0, if I'm not wrong. 2 1 2 0 are the diagonal elements. Now one member of this diagonal elements we will take, and that will be 3 comma 3. Okay, I and j, let's take an example wherein I and j value are 3 3. Okay, so the value which has to be returned is 2 now in this case. Okay, now let's work about this. So this is actually your exceptional case, so wherein the user has to enter the value between 1 to n. Other than that, if he enters, he's gonna get a exception, and based on that he can re-enter the value, so it will work properly. Okay, for handling the exceptions, this function is used. Now this is your proper function wherein we are using switch function. Now as addressed, I value and j value are 3 and 3. Okay, so we use switch of I minus j. Switch of I minus j gives you now 3 minus 3, 0 it becomes. So case of 0 will run. Case of 0, we have return element of. So if it's a diagonal, if it's a main diagonal element, then use this function to return the element from the mapping function. So we use return of element of n plus I minus 2. Now let's try to work on this. So the element which we are supposed to return is 2, and we will concentrate on that one dimensional array. So we are indeed supposed to pick which position element. Okay, so we are using n plus I minus 2. So n is 4, and I is 3, and you have 2. So 4 plus 3 minus 2, you get 5. So fifth position we have a element 2, and that's correct. That is correct. Fifth position 0 1 2 3 4 5. Fifth position the element is 2, and this 2 will be returned. So that's correct if you're having any element on to the diagonal. Now let's look at the diagonal below the main diagonal. Okay, so for that we will take an example 3 comma 2. 3 comma 2, wherein I is equal to 3 and j is equal to 2. This is valid for a diagonal below the main diagonal. For this, what happens, what will be its equivalent position in the element array we will look at. So now I is equal to 3 and j is equal to 2. So you come here, let's work on this. I minus j, so it becomes 1 1. Case 1 will be executed. So case 1 you have return of 3 minus 2, return of 3 minus 2. So it is return of element of 1. So element of 1, when you observe, the value is 5, the value is 5, and the position 3 comma 2, the value is 5 in the two dimensional 3 comma 2 position will be located onto position number 1 in your array, and that's correct. Okay, similarly the last case, if required, we will look at the element 2 comma 3, 2 comma 3, wherein I is 2 and j is 3, and this has a element 3 in the two-dimensional space, and where it will be aligned to in the one-dimensional, we will check it out. Okay, so 2 comma 3, which index you are talking about? So you use now case of -1, case of -1, so you return element of 2 times n. So 2 times n, it becomes 2 times 4 plus I is 2 minus 2. Okay, so it is 8. Position 8 you can check. Position 8, when you check, this answer is 3, and that's correct. So 8th position you have 3, and that is actually the data which will be grabbed, okay, using the mapping function. Mapping function is not defined, but the program is fine. So this is what get is. So only one function if you look at, that's fair enough. Then we will move on to triangular matrices. In the triangular matrices, you can concentrate on the figure 7.7c. How many number of non-zero elements you have, and how many number of zero elements you have. So simplest definition of triangular matrix. First we will talk about lower triangular matrix. Lower triangular matrix, the elements below the main diagonal, I repeat, the elements below the main diagonal would be non-zero, and all the elements above the main diagonal would be 0. Okay, all the elements above the main diagonal will be 0, and all the elements below the main diagonal will not be 0. That's the definition of lower triangular. Similarly upper triangular, it is other way around. Okay, so here we will strictly look at the simple function set implemented to grab a data from a two-dimensional space matrix of a lower triangular matrix and map it onto a one-dimensional array. The mapping function will not be discussed again, but the program, how it is going to map, we will discuss about that. One more thing to note here, statement number 2 talks about how many number of space we need to create for a upper triangular or a lower triangular matrix. If we look at an example 7.7c 4 by 4 matrix, if we consider upper triangular or lower triangular, this case let's focus on lower triangular. So lower triangular elements are read, just concentrate. We have 2 0 0 0 as the first row element, second row elements 5 1 0 0, third row element 0 3 1 0, fourth row element 4 2 7 0. So altogether 4 by 4 matrix, how many non-zero elements you have? Approximately it is equal to 10. And how is that you're gonna get it? And it is given by this formula. It is 4 into, use this formula, 4 into 5 divided by 2. So 20 by 2, that's 10. So this many number of space should be created. You are using lower triangular or upper triangular. This is the capacity of your one-dimensional vector which you are going to create in the data structure for mapping. Okay, so here the one mapping which is discussed over here is row based mapping is discussed, wherein based on the row you scan elements according to row, and the non-zero elements will be outputted onto the array. Okay, so when you look at the lower triangular matrix, first row only one non-zero element you have, and that is 2. So 2 will be picked first. In the second row you have two elements, so scan from left to right, you have 5 1 as the non-zero element, so those two will be picked in the second row. In third row you have 0 3 1, those elements again will be picked in the third row, and the finally fourth row have four elements now, 4 2 7 0. So this way the elements will be picked and it will be stored in the position 0 to 9. Okay, now let's look at the function program, the program what you have for lower triangular class. Okay, for lower triangular class we have the function defined as let's not worry about this. This is for the user has to enter a proper number. Provided if he enters a proper number, then this information is not required. Ensures that the user enters a value not less than 0 and also not greater than n. So within the boundary, if it's then only this function will work. If not, this message will be thrown. Okay, so let's take an example wherein we will concentrate on a lower triangular matrix. 4 comma 1 position we will take. 4 comma 1 position, row is 4, I is 4, and j is equal to 1 I'll take. Okay, and that position right now the element what you have is 4. 4 is the element where it will be mapped onto the one-dimensional array we will look at, and also how to modify that, how to modify the content at this position. That's what it does. Okay, so here we have the value of I as 4, the value of j as 1, and let's say that the new value which needs to be stuck on to this position addressed by the two-dimensional vector space is 4 and 1. Okay, so this number, let us take the number as 10. 10 should be replaced where you have 4. Okay, so new value is 10, old value is 4, that is located at the position 4 1. This will not be executed. Now you check this condition. If I greater than or equal to j, is the value of I greater than or equal to j? Yeah, I value is 4. Okay, and it is greater than j. So then return this. So evaluate element of I value is 4 into, then you have the value I minus 1, so you have 4 into 3. Okay, then you have divided by 2 plus 1 minus 1. So denominator you have 2 and numerator you have 12. So position you get as 6. So sixth position, if you scan and the one-dimensional array which you have addressed, you are going to get the value 4, and at that location 10 will be the value which will be replaced, and that's what this does. This is the simplest example how this functions. So you may have to remember this equation, this formula needs to be looked in if you want to load a new value onto this location using this two coordinates and getting it converted into one coordinate. Okay, and this is about lower triangular. Finally we'll come on look at the sparse matrix. The sparse matrix, we define the sparse matrix as a matrix wherein majority of the elements are 0 and only few elements are non-zero. Simplest is our definition, and we call the matrix to be dense if the number of non-zero elements are more than the number of zero elements. Okay, so we can say sometimes tridiagonal matrix and diagonal matrices are sparse matrices. Okay, but lower triangular and upper triangular you cannot call it as a sparse because many elements are also non-zero there. Okay, it's approximately equal somewhere down the line, the number of zero element and number of non-zero element. So you cannot call literally triangular and upper triangular or lower triangular as a sparse matrix, whereas definitely diagonal and tridiagonal are sparse matrix. Now how do you represent sparse matrix using linear list? Well, this question was asked many times occasion. Just we have to discuss the way. So the way you store the sparse matrix value, which is can observe here, you have a 4 by 8 matrix and how it will be stored using a linear list representation. So in the linear list representation we will use three variables: row variable, column variable, and value. variable. So when I talk about row variable, column variable, and value variable, you will definitely understand what exactly I'm trying to convince. So it talks about the first row, how many elements you have with non-zero, that needs to be picked, value needs to be picked. So here first row, okay, and first row and fourth column, okay, first row fourth column you have a value 2. So just take its root coordinate, column coordinate, and the value. That's your first term. Okay, term 1 has 1, 4, and 2. What is 1? 1 is the row index. Row index, first row, and 4, fourth column, first row, fourth column, element is 2. That's how it is picked. Similarly, 1, row 1, this element, 2 element, okay, I mean this element 1 is located at first row and seventh column. Okay, so that is there here. Value is 1, 1, 7, 1. Similarly, repeat the process. So this is how you represent Sparse matrix using linear list representation. If interested, you can write a program which takes the, which when given as this input, you have to produce this as the output. So if possible, you can write a program. If required, I'll just put this program in the block. Okay, in the Moodle I'll upload if required. Okay, next we will look at simple header. This was discussed once, so nothing exactly it does. And transpose and add functions we have for this Sparse matrix. The reason why the previous slide which was addressed here is not acceptable, because this takes more memory locations. Even though you have this much element, the total number of space required will be the number of elements into 3. This many number of space needs to be created for storing this kind of data. Okay, so that's not more convenient, but still if required, we can discuss about that. Okay, so this header was asked, but transpose and add function will not be asked if I'm not wrong. Okay, so this does what? So transpose and add template you can take, just for the time being, take down this header of the Sparse matrix which is having transpose and add method, and literally what it has to do, it has to take the Sparse matrix element and it has to transpose the Sparse matrix, and add method would add two Sparse matrices, element wise it will add. Okay, that program is to be addressed. Okay, so that's stuff which we have. We will work on stack in the next slide. Probably in the next forthcoming lecture we will work on stacks and also queues. Fine.